Hi, this is Abhilash, and today we are going to solve another problem from LeetCode 684, redundant connection. So in this problem, a tree is an undirected graph that is connected and has no cycles. So we are given a graph that started as a tree with n nodes labeled from 1 to n with one additional edge added. The added edge has two different vertices chosen from 1 to n. So in this case, we are chosen from 1 to n. And was not an edge that already existed. So adding this edge actually creates a cycle in the graph. So the graph is represented in the form of edges, edge connections, AI and BI, and we have to return an edge that can be removed so that the resulting graph is a tree of n nodes. So in the figure that we see over here, 1, 2, and 3, we can remove any one of the edges, either 1, 2, or 2, 3, or 1, 3, so that it becomes connected and a tree. So explicitly, 3 edges are not required for 3 vertices. So this is a cycle. So the problem can be formulated as we have to detect a cycle in the graph. And this is the main part of the problem. And the second part of the problem is that we have to return, since we have to return a vector of n, so we have to return a pair of vertices, that means an edge or an edge, which can be removed. So what will happen after we remove this edge? So cycle will no longer be there. So we have to return that particular edge. That means that particular edge, which upon removal will lead to a tree. So if we are going from one node to another node via a cycle, so we can just simply return the last edge or the last two vertices which are forming that particular cycle. In this case, if we start from 1, 2, and 3, we can go from 1 to 2 and 3, and we see that after 3 comes 1. So we can, this is the last particular unvisited node at that particular point, and we can take this 1, 3 as our output, and that will resolve this particular use case. So one way of solving is to apply DFS, right? And how will we apply DFS? So the DFS can be applied by taking one edge at a time. So what we are doing, so we are trying to find that if adding a particular edge to a particular graph, whether it creates a cycle. So we have to check whether adding an edge to the graph creates a cycle or not. So this is the entirety of the problem. So whenever we see that if we add an edge and it creates a cycle, then we can be assured that we can remove that particular edge. Okay, so now that we have understood the idea about it, we can begin the implementation. Since we'll be going through the DFS approach, it will be a Boolean function to check whether a node, if there is a cycle or not, whether the addition of a node is creating a cycle or not. So we'll be creating an adjacency list representation because we need the complexity to be of O of E plus V, of O of N in this case. So let us take a vector of int and let us write this as adjacency list, and let us also create a variable to denote the number of connections or the number of edges or vertices in the graph. So we are adding a +1, the reason being 1 to n. So this is very interesting and important. So we are going to keep it n over here, and for this is our this will be our input adjacency list. We also need an output result, so that will be a vector of int, and write it as v. And we also need another particular array or a vector which is known as the visited array, which is quite common in DFS. So visited vector. So, and this visited vector will have a dimension of n plus 1. So the edges size plus 1. So v of n essentially. So in this case, we are going to initialize, let us take this as a bool so that we can initialize everyone to false, because we can start with a false node, right? Now, once we have done this, we can iterate over the edges. So we can go from I equal to 0, I less than n, I plus plus, right? Or this can be edges dot size plus plus, and we can append in the adjacency list. So we can append the edges I0. This is our U node if you want to write it in a shorter form. Since this is bidirectional, that means both of them, this is an undirected graph. So either we have to push them 2 times in inverted order. So let's say I0 and I1. And in the next case, I'm going to copy this and paste it here. 0 and 1. So now our actual BFS loop should work. Now, since we are adding each edge one by one, so we have to do certain checks. Okay, so the first check is going to be, I'm going to check if a particular function, let's say DFS cycle, let's rename that function. If DFS cycle is true, then I'm going to return, I'm going to add this to the vector, because if DFS cycle indicates that if DFS cycle is true, that means adding that particular edge or a pair of vertices is causing a cycle in the existing graph. As simple as that. So in this case, we are going to apply this logic, and we are going to append it to the final vector. So we're going to push back what is the output of that particular vector. So this will be our final result, and we're going to return V. Now let us write the DFS function first before returning. So it will be a Boolean function, DFS cycle. So it is going to take the vector of int. That means that adjacency list, which is the graph in this case. It will also take the visited array. It is a bool array. Okay, bool array, which is visited. Okay, we are going to take 2 more things. That is the current index. Let us write it as IDX, and the parent. Okay, we can also write this as V for simplicity. So the parent. So at each step when we are adding a node, we have to fill in this particular function as well. So adj list visited, and after that we have to add the vertex. So in this case, it will be edges I, this particular part, edges I comma I0. That is the node that is being currently visited. And we're going to take -1 as the parent, considering this as the root. So our DFS logic should look like this. Now we have to write the function or logic for cycle detection. Okay, so the logic for cycle detection starts like this. For each node, we mark as visited equal to true. Okay, visited for that particular vertex V as true. Next step is iterate through the neighbors. Neighbors indicates iterate through the adjacency list of the V. That means the vertex in this case, and check if let's say V is not equals to the parent. That means the children of these, that means the neighbors, any one of those neighbors is not equals to the parent. So if it is equals to the parent, then a different case might happen. And if it is unvisited at the start, then we can so in this case, we will be checking if the neighbors is not equal to parent, then that indicates that it is a true. That means the logic is true. And in the next case, we'll be checking whether if the DFS functions returns true, then it is automatically as true, because it is a recursive function in DFS. And after each visited is completed of a particular node, we can mark that visited of that particular node as false. This ensures that when I'm adding a separate edge on the pre-existing edge, I will not like mark it as visited from the start. Okay, so this ensures that while I'm adding the edges one by one, the DFS cycle is checking at each step. This particular function gets checking at each step with the resulting graph. So at each step, so let's say 1 to 2 gets added, and then 2 to 3 gets added. So at each step, it checks whether the cycle is getting formed or not. So this is the idea. So to do this, let us start as visited of that particular node, that is V equal to true. So this is my first step. The next step is to iterate through all the items in the neighbor of V. That means the adjacency list representation of V. So if the node is not visited, so let us write it like this way. If node is not visited, let's say J, then what we're going to do, we are going to apply a check. So here we are checking if not visited. Okay, and here we are going to check another different condition, which is if the adjacency list, if the current node J, and using that the DFS of J, so let's say DFS of J is true. So if DFS of J is true, that means there is a cycle in the graph. Okay, so that means if I write over here DFS of ADJ list, okay, and then visited, and after that the current index, which is J, and its parent, which is V, because J comes in the adjacency list of V. If this is true, then cycle. So I'm going to return true over here. Okay, now outside this there is an else, there should be an else condition. Now this is a very important condition. If we can write and else if, let's say if the current J not equals to parent, okay, so in this case we are going to return it as true. This is also detects a cycle. Okay, now after this is done, outside this we are going to keep visited of that particular vertex V as false, and we are going to return false. So this should be our checking functionality of the entire like DFS cycle checking functionality. So it will check upon adding a particular edge whether a cycle is getting created or not. Okay. So after this is done, this function is created, we can use this logic over here. So in this case, we are going to push back each and every node which passes this particular test. That means if DFS cycle is true, we are going to push it in the vector. So for this, we are going to push back edge is I0 and its corresponding another vertex, which is edges I1. Okay. Now, once this is done, this particular item will be there in the vector, and we can return that particular vector. So this is for checking whether adding an edge causes a cycle to form in the graph. Okay. So this should be our entirety of the function. This is very important because this ensures that for next iteration, the nodes are like unvisited or false. Okay. So there are again alternate ways to do this particular trick, whether we can use a particular set or a map kind of a structure where we can check whether a node has been visited or not by just doing set.find or map.find. Okay, so that is an alternate strategy. But if you want to reduce the space to just a one-dimensional vector, you can also use this particular logic. So if we were to run this code and check the output using this logic, so I see that, yeah, so I have renamed this function here correctly. So this is a very interesting problem from a different perspective, because in this case, we are not only checking for the graph, cycle in the graph, but also iterating by adding each edges in the graph. Okay, so I have renamed this as phi both the times, so this should be visited. Okay, let me just check the variables if they're okay. This should be okay to run. So for this particular graph, we see that it is getting accepted, and it is saying that 2,3 can be removed. Now this is quite evident, because if we can put into the steps which is happening, let's say we are I'm doing a C out in this case. to what are the intermediate steps which are getting current visiting node, current visiting edge rather. So if I just write this like this, edges I0 and a little space, let me write it as like this, edges I1. Okay, so let me run this code to understand at what each level is doing. So we can see that as the DFS fills up, 1,2 is getting filled up, 1,3 is getting filled up because it is in the adjacency list representation of 1. So 3 is there. So 3 is already visited. Now when 2 tries to add this particular edge, that is 2 to 3 edge, a cycle gets formed. And a cycle gets formed, that means that DFS of cycle returns true. Okay. Now, why does this return true? Because if j not equals to parent, this gets triggered in one iteration back. So this particular use case, j is not equal to parent signifies that there is a cycle. That means that if I'm traversing a particular node and I see that a previous node is already visited, then that indicates that it is a cycle. So if I try to submit this and let me see whether it is passing all the test cases or not. So I see that it is a wrong answer. So the output is 1 and 4. Okay, so we have to always return the top 2 elements. That means the top 2 elements. So let's say in this case, we can return that. So in this case, one way we can do this, since we're adding to the vector, so it will add all the edges which are getting created in this manner. So in this case, we can try to return this at the very step itself, at the first step itself. So let's say 1,4 and 1,5 both are valid answers, because if we try to draw this graph and if we try to see the results, we'll find that 1,4 and 1,5 both are creating the cycles. So, but we can return only one of them. So in that case, we can just add a break statement and check whether this is giving a correct result for this particular test case. Let me copy this particular test case and let me just run it just to see whether it works or not. So ideally this should work because we are breaking at the first instance where a cycle is getting created. And let us try to see whether it is getting a solution or not. And it is getting a solution. So this should not be a point of concern. The test cases should be running and the logic should be very sound. If we didn't give any break statement, then it would have given all possible cases where a cycle would have existed for that particular edge. So in the previous example, we saw that 1,4 and 1,5 both gave rise to a cycle. So we have to break on the first instance that we see to get the answers accepted. So that is all for today. This is quite an interesting problem considering the algorithmic approach. So we are applying DFS. We are checking at each step whether if we add a particular edge in the graph, whether it is creating a cycle or not. So just on a final note, if the complexity analysis can be O of V plus E, because simply it's an adjacency list representation, or in this case, O of N. So number of nodes or vertices in the particular graph. Now, this is a very good problem for cycle detection in DFS, and I hope to see you in the next video.